All right, we're on our last couple of videos here. So we can use all this information about the renal clearance of drugs to predict drug and disease interactions, and therefore know what we need to do to try to anticipate these and change our dose rate to avoid toxicity or lack of efficacy. So the first thing we have to do is figure out how the drug is cleared to be able to anticipate this and know what drug and disease interactions can occur. So here's a potential case. Your patient is taking digoxin. Digoxin is an antiarrhythmic. It also slows the heart rate so that it can be a little more efficient in how it pumps. The total clearance of this drug in your patient is 190 mils per minute. Volume per time, just as we would expect. You know from the literature that 68 micrograms of a 100 microgram dose of this drug is recovered unchanged in the urine. So that shows us how much is cleared by the kidneys. If it's unchanged in the urine, that means it's not metabolized. Therefore, it is cleared by the kidneys. You also know that digoxin is 25% bound to albumin in the plasma. So that means the fraction unbound is 0.75 to albumin. Okay, it's not very highly bound, so we don't have to worry too much about binding changes. Okay, so what are the predominant processes and what drug and disease interactions do you predict? Okay, well, 190, let's get a little piece of paper here. So 190 mils per minute is our total body clearance. We also know that 68 micrograms of a 100 microgram dose are recovered unchanged in the urine. So that tells us that this fraction is our FE, or our fraction excreted unchanged in the urine. So I don't need a calculator for that, right? Our FE is 0.68. which means 68% of the clearance is due to the kidneys. The remainder is metabolized. So this is renal. So how do we get renal clearance? Well, renal clearance will be total body clearance times our fraction excreted unchanged in the urine. So for this drug, we are given that the total body clearance is 190 mils per minute, and that the FE we just figured out is 0.68. So what is our renal clearance then? Okay, this I do need a calculator for. 190 times 0.68 is 129. Clearance renal is going to be 129.2 mils per minute. So if that's the case, we can compare our renal clearance to our filtration clearance and be able to figure out if this is predominantly secreted or predominantly reabsorbed, can't we? So how do we determine our filtration clearance? Well, our filtration clearance is equal to GFR times our fraction unbound. Well, we're given, let me use a better color because really you can't see that, Sandy. So GFR is standardly 125 mils per minute. That's a given. And the fraction unbound of this drug is 75%. So what's 75% of 125? Let's see. The filtration clearance is going to be 93.75 mils per minute. So if 93.75 mils per minute are coming in through the glomerulus, so we know that in through the blood into the glomerulus, and out here the filtration is 93.75 mils per minute. And we also know that at the end of the line, when we get to the end of the nephron, 129.2 mils per minute is coming out, is being cleared eventually. So this is bigger, isn't it? So more drug is going out than came into the nephron. So what has to be the predominant process? There must be drug added. So the predominant process must be secretion. So there must be drug added to the nephron from the blood. So we know the predominant process is secretion for this drug. So what are the anticipated drug and disease interactions? Well, if it's secretion, remember secretion is an active process. And if you remember, if this is our blood and this is the nephron where we're making urine, right? So this is the nephron. With active secretion, we see drug being moved from the blood into the urine. But it needs a ride. It needs a transporter to go. So the digoxin is moving from the blood into the urine, right, with a transporter. So what drug and disease interactions could we have? Well, what if another drug that is cleared by the kidneys and is predominantly secreted, so cleared renally, is secreted and competes with our digoxin for these carrier sites. Remember, acids compete with acids and bases compete with bases. And I think digoxin's an acid. I'll have to go back and look, but I think digoxin's an acid. So if it's an acid, we're going to be looking for another acid that is secreted and cleared by the kidneys that has a lower KTS, that has a higher affinity for this transport site. Because if it has the higher affinity for this transport site, what's going to happen to our dig? Our digoxin is not going to get that ride. It's not going to be able to go into the urine. It's going to stay in the blood, isn't it? So what does that mean? That means that you have a decrease in your renal clearance, which is a decrease in your total body clearance, which increases CSS average and increases half-life. And that could cause toxicity, couldn't it? So the drug interactions that I'd be looking for is another drug that's cleared renally, secreted, and is another acid that has a lower KTS. The other possibility would be a drug that you're already on, so the patient's on digoxin and another drug that already has these characteristics, and if you stop that drug, then there was no longer competition, then digoxin could start getting a ride into the urine, which then the opposite would all be true, right? Then clearance would increase because it's going now, getting a ride out into the urine. Total body clearance would increase, your CSS average would decrease, and your half-life would decrease. So you could be at risk now for lack of efficacy. Okay, so that's how we look at these things.